Section: Introduction. In this section, we discuss our advancements in view synthesis, which have recently produced impressive photorealistic results. Our approach involves two main steps. First, we optimize to create a 3D representation of a scene, and second, we render this representation from a new viewpoint. While some methods can render in real time, the reconstruction process often remains slow. We introduce a neural algorithm that combines both reconstruction and rendering at real-time speeds. Our algorithm takes a set of high-resolution images or video streams as input and generates high-quality novel views. In our experiments, we utilize 8 images per frame, spaced 30 centimeters apart, and demonstrate that our model can produce novel views at 30 frames per second with a resolution of 1080p on an NVIDIA A100 GPU. Through detailed analysis, we show that our method achieves state-of-the-art quality at real-time rates, even rivaling some of the best offline methods. We validate our design choices through extensive testing, revealing that our network is highly adjustable and can achieve even better quality at slower rendering speeds, such as 10 frames per second. Our approach incorporates several key concepts, which we outline below. We utilize a layered depth map, LDM, for our 3D scene representation. The LDM consists of a small number of layers, each with its own depth map, density map, and blend weights. The depth map captures the geometry of the scene, the density map handles occlusions and smooth edges, and the blend weights help produce high-resolution images. Unlike previous methods that require a layered mesh, we optimize the LDM for each specific view in a video sequence, allowing us to generate depth, density, and blend weights tailored to that view. To efficiently solve the LDM for each frame, we employ a multi-scale learned render and refine network. This method, inspired by earlier work, converges much faster than traditional approaches. In each update and fuse step, we render the current LDM estimate and refine it based on the results. Our implementation is the first to achieve real-time performance by integrating these steps into a U-Net structure. The network processes image features through a multi-scale pyramid, starting at a low resolution and progressively refining the LDM. We reduce the number of layers in later iterations, as most scenes can be effectively represented with fewer depth impulses. While reducing layers slightly impacts quality, the significant gain in speed makes it worthwhile. Our architecture efficiently balances computation between spatial and depth dimensions. Finally, we generate an LDM at a lower resolution and upscale the attributes using bilinear interpolation, which effectively maintains smooth regions and sharp edges. Section Summary. In this section, we present a neural algorithm that enables real-time reconstruction and rendering of novel views from high-resolution images or video streams, achieving 30 FPS at 1080p resolution. Our approach utilizes a layered depth map, LDM, representation and a multi-scale learned render and refine network, allowing for efficient optimization tailored to specific views while maintaining high-quality output comparable to top offline methods. Section: Transformer-based input view fusion. In this section, we address the challenge of efficiently combining information from multiple views in view synthesis. Our approach integrates a transformer-based network component during each update and fuse step. While similar methods have been effective in the past, they can be costly. We present a new, optimized version of cross-attention called one-to-many attention, which significantly reduces computational demands. Additionally, we replace the traditional positional encoding in transformers with a directional encoding based on the poses of the input images. When we combine these innovations, along with other design choices detailed in our paper, we create a new algorithm that generates high-quality synthesized images in real time. Our method targets novel view synthesis, where we generate a new view from a set of input images taken from different angles, capturing complex 3D effects and occlusions. Traditional methods are often categorized as image-based rendering, IBR, while newer techniques using neural networks fall under neural rendering. Our approach is a neural rendering method that leverages IBR to efficiently produce high-quality, high-resolution results. We focus on recent neural rendering advancements, as classical methods are well documented in existing surveys. Key features that set our approach apart include its physical representation and our efficient neural algorithm. The effectiveness of view synthesis algorithms heavily relies on the accuracy of their physical representations. Recent methods utilize various representations, such as implicit surfaces, point clouds, and volumetric ray marches. The best-performing algorithms typically use fully volumetric representations, which capture complex geometries better, although they can be slow. While there are recent techniques to speed up ray marching, only one, NRF, achieves interactive rates for both reconstruction and rendering while maintaining competitive quality for certain scenes. Our work employs a layered depth map, LDM, representation, similar to layered meshes, but we render the LDM directly without a mesh, enhancing efficiency. The algorithm we use is designed for efficiency and generalizability, allowing us to reconstruct a wide range of scenes with fewer input images. Unlike many recent methods that require separate training for each scene, our approach is generalizable, producing high-quality results even with a small number of images. We compare our method with 3 state-of-the-art techniques, highlighting how our approach effectively aggregates information from multiple views. Earlier methods often relied on simple concatenation of features, which lacked order invariance. While recurrent networks allowed for variable input numbers, they still faced order issues. Statistical measures like mean and variance are simple but limited. Our proposed one-to-many attention combines the efficiency of previous methods while retaining expressive power. We compare our method with GPNR, which also aims for high-quality results using a generalizable neural network. Although GPNR extracts patches from neighboring images, our one-to-many attention is optimized for better performance, achieving competitive quality while being significantly faster. We also evaluate NRF, the fastest generalizable neural rendering method, which samples around a single surface. Our results show that we achieve higher quality for more complex scenes while being much faster. Lastly, we compare with Simply, noting that our multi-scale LDM architecture and attention module lead to superior quality and speed. Section Summary. In this section, we present a transformer-based approach for efficient view synthesis that incorporates a novel one-to-many attention mechanism to reduce computational costs while maintaining high-quality output. Our method leverages a layered depth map, LDM, representation for effective scene reconstruction and demonstrates superior performance compared to existing algorithms, achieving real-time rates and high-quality results even with a limited number of input images. Section: Single-View Methods. In this section, we explore single-view methods for rendering 3D scenes from limited perspectives, such as a single image or a video stream. These methods include generative algorithms with learned prior knowledge, explicit priors like human figures, and techniques that utilize multiple views over time. While these approaches are promising and can simplify image capture, we note that multi-view methods, as discussed in previous sections, generally yield better quality and versatility across various scenes. Therefore, we categorize single-view methods as a distinct group and do not directly compare them in this paper. Next, we outline the key components of the Quark algorithm. To achieve high-quality results in real time, we design our network to perform a multi-scale iterative process of rendering and refining, primarily at low resolution. Initially, we encode the colors and ray directions from the input images into a feature pyramid. These multi-scale features are then processed through a series of iterative updates, which refine the layered depth map, LDM. This process is efficient as it balances the increase in resolution with a reduction in the number of layers. During each update, we render the LDM to the input views and aggregate features using a one-to-many attention mechanism. Once the iterative updates are complete, we produce a final LDM that is 4 times smaller than the desired output resolution. We then render this LDM to a full-resolution view through a lightweight process. This involves bilinearly interpolating the LDM attributes to the output resolution, projecting the original input views onto the depth layers, and blending them to create the final image. If necessary, we can also generate a depth map by compositing the decoded depth instead of the blended views. We will delve deeper into these stages, starting with the LDM output representation and rendering equation, followed by a comprehensive description of the algorithm that generates the LDM. We will also elaborate on our transformer-based fusion mechanism and detail our training procedure. The layered depth map, LDM, produced by the Quark network consists of 21 layers, each with spatial dimensions of 22. These layers are positioned within the frustum of the target viewpoint. Each LDM layer has 3 attributes: depth, density, and blend weights. The depth and density represent depth and transparency values, while the blend weights contain coefficients for blending the input images on each layer. To render the target image from the LDM, we back-project the input images onto the depth layers using a specific operator. The back-projected images are blended with their respective weights to create per-layer RGB values, which are then composited to produce the final image. We utilize a standard over composite operator for this process, allowing us to render images efficiently. During training, we use standard differentiable rendering components, but for inference, we employ a CUDA-optimized renderer, achieving 1080p resolution at approximately 1.3 milliseconds per frame. In this subsection, we detail the 3 main components of the Quark algorithm, emphasizing the iterative multi-scale render and refine approach. We encourage readers to refer to the figures for a clearer understanding. Our method avoids the computational expense of solving the LDM directly at the final output resolution by first downsampling and encoding the input images, followed by iterative refinement over multiple update steps. This multi-scale strategy is crucial for the speed of the Quark network, as it allows us to perform computations at low resolution in early iterations and gradually increase resolution while reducing layers in later steps. Section Summary. In this section, we describe the Quark algorithm, which utilizes a multi-scale iterative render and refine process to efficiently produce high-quality layered depth maps, LDMs, from input images, balancing resolution and layer count to optimize computation. The LDM consists of multiple layers with attributes for depth, density, and blend weights, allowing us to render novel views quickly and effectively. Section: Encode input images. In this section, we describe how we encode input images. We begin by converting the input images into low-resolution feature map pyramids, each with levels of 38 by 38, using a standard convolutional encoder. This allows our model to work with reduced resolutions instead of the original images. During each update step, we select the appropriate resolution feature map from these 38 by 38 maps. Additionally, we encode the direction of image rays in relation to the target camera using a ray directional encoding. This encoding helps the network focus on input views that are closer to the target view, which enhances the results for reflections in surfaces that do not follow Lambertian properties. We have seen various methods for encoding ray directions, such as sinusoidal positional encoding and spherical harmonics. However, due to the geometry of our model, we can use a simpler approach. We compute the difference vector between where the ray intersects the near and far planes of the model's frustum in projective space. After applying a tanh function to this two-dimensional difference vector, we use sinusoidal positional encoding. This method has several advantages. It returns 0 when the input ray aligns perfectly with the model's ray. It focuses on ray directions that intersect within the frustum bounds, and it still represents rays outside the frustum, albeit with less precision. For efficiency, we compute the ray directional encoding once at low resolution and then upsample it to match the dimensions of the feature map pyramid. We utilize 8 octaves of sinusoidal encoding and project the result to 40 channels, applying a separate projection matrix for each resolution needed. Next, we move to iterative updates. Our network progresses from coarse to fine resolution through 5 update and fuse steps. During this process, we handle the model in an encoded form known as the feature volume. The number of layers and the spatial resolution of the feature volume change with each update step. We increase the resolution while decreasing the number of output layers, similar to a U-net, while keeping the number of channels constant. Each iteration involves calling an update and fuse network block, which decodes the feature volume to create an intermediate model by extracting depth, density, and appearance features. We then bilinearly splat the density and appearance into each input view, avoiding costly ray tracing or rasterization. Finally, we overcomposite these layers to generate the rendered image for each input view. The rendered model is combined in the update block with the corresponding input image features and encoded ray directions, which we select from the two-level image feature pyramid. If there is a resolution transition, the update block may include an upsampling step. It then produces update features using a small CNN and back projects these into the feature volume. This array of update features encodes both the extracted image features and visibility information from comparing the rendered model to the input images. We aggregate these per view update features using several fusion blocks, where each block applies one-to-many attention to fuse the back projected image features, followed by residual CNNs to update the encoded model. Finally, to render the intermediate model, we decode the feature volume to instantiate it. We decode density and depth similarly to how we do for the final model, but we activate before projecting to the views. Instead of using blend weights, we instantiate the intermediate model's appearance directly. When rendering, we project the intermediate model layers through the depth map into each input view and overcomposite the results to yield the final output for that view. Section Summary. In this section, we describe how we convert input images into low-resolution feature map pyramids using a convolutional encoder, allowing the model to work efficiently at reduced resolutions. We also explain our ray directional encoding method, which enhances the model's focus on relevant input views, and detail the iterative update and fuse process that progressively refines the latent diffusion model, LDM, through a series of updates and fusions to produce rendered images. Section: Layer Collapse. In this section, we discuss our approach to layer reduction and initialization. Before the last two update and fuse steps, we cut the number of layers in half using a straightforward residual multilayer perceptron. Here, the direct path averages adjacent layers, while the residual path combines them. This layer reduction leads to a slight drop in quality but significantly decreases computation during high-resolution iterations. For initialization of the learned depth model, LDM, we apply a specific version of the update and fuse step. Since there is no existing LDM at the first iteration, we begin with a single learned feature that has 40 channels, which we expand to initial dimensions of 50 by 50. We also assume the depth layers are flat, using predefined depth anchor values, and we skip rendering the image at 42 by 42. This results in a simpler update block that focuses on merging image features and ray directions. After the update and fuse steps, the feature volume represents the final scene, though still in an encoded and relatively low-resolution form. We decode the final LDM from dimensions of 51 by 51 using linear projections followed by nonlinear activation functions. Specifically, we decode density using a learned set of linear weights. When decoding depths, we ensure that the resulting LDM layers are evenly spaced within the near and far planes of the target view. We calculate depth relative to depth anchors, which are the center points of each disparity band. We compute blend weights using a one-to-many attention mechanism similar to that in the fusion blocks, but we delay applying the softmax until after upsampling to the target resolution. This step is part of the final fusion block and utilizes the image update features from that block. All activations occur after bilinear upsampling to the final resolution. For real scenes, depth and density are usually smooth, and post-sampling activation can create sharp occlusion boundaries, while blending over full-resolution images yields high-resolution RGB output. Next, we describe the one-to-many attention mechanism in the fusion block, which combines the update features to create an updated feature volume. We employ a novel one-to-many attention block that aggregates per-view update features by cross-attending from a single aggregated feature to our per-view update features. This attention mechanism selects the most relevant information from the update features, incorporating both image matching cues and occlusion. The ray directional encoding within the update feature helps the network focus on rays closer to the target view. We adapt the standard attention operation to aggregate across view features. The typical attention operation computes the output based on a set of queries, keys, and values. In a full transformer, multi-headed attention projects these into multiple heads before performing attention queries. We modify this to cross-attend over the update features. The standard multi-headed attention requires numerous matrix multiplications, but we identify a redundancy in the formulation. Under certain conditions, we can eliminate these multiplications on the update features, leading to a more efficient approach that focuses on dot products and sums instead. This optimization significantly reduces the computational load, especially for the number of inputs and heads we use in our attention blocks. Our one-to-many attention method avoids matrix multiplications on the update features, shifting most computations to image space and elevating them to 3D. Section Summary. In this section, we describe our approach to reducing computational complexity by halving the number of layers before the final update and fuse steps, which slightly impacts quality but significantly enhances efficiency. We also detail our optimized one-to-many attention mechanism that effectively aggregates per-view update features while minimizing matrix multiplications, leading to improved performance in processing depth and density for high-resolution outputs. Section: Fusion Block. In this section, we describe the fusion block, which is part of our pre-layer norm transformer. This transformer includes residual self-attention blocks followed by residual MLP blocks. We define the one-to-many attention block, which incorporates normalization, and it mirrors the MLP block of the transformer. This one-to-many attention module is combined with residual convolutional blocks. The complete fusion block, which includes both the one-to-many attention and convolution blocks, is repeated multiple times within each update and fusion block. This design helps us aggregate information across different views and keeps the latent diffusion model, LDM, aligned with real scene structures. For training, we use a set of calibrated multi-view images from various scenes. Specifically, we train our network using 8 input views that are randomly selected from the 16 views closest to a target image. Our model is trained with a combined loss function, using a batch size of 16 on a single machine. We conduct 250,000 iterations at half resolution before moving to full resolution for an additional 350,000 steps, totaling 600,000 steps. To manage memory and training time, we crop the target and rendered images to 256 by 256 pixels during low-resolution training and to 512 by 512 pixels during high-resolution training. The learning rate is gradually increased over 20,000 iterations, remains constant for 520,000 iterations, and then decreases to 0 over the final 680,000 iterations. We apply residual scaling throughout our model to enhance stability. We train our models using a weighted combination of several datasets, including spaces, RFF, Next Shiny, and SWORD, with equal weighting for most datasets and a lower weight for the smaller Next Shiny dataset. Since these datasets have different image resolutions, we adjust the aspect ratio of the internal LDM dimensions accordingly, ensuring consistent computational requirements. We also adapt the near and far planes for each example based on the depth distribution from reconstructed points. We developed 2 model variants: Quark, which starts with a lower LDM resolution and reduces layers while increasing spatial resolution, and Quark Plus, which begins with a higher resolution and maintains more layers. Both models target a 1080p image size, requiring different upsampling factors during the final output stage. In our results, we provide both qualitative and quantitative evaluations that showcase our method's effectiveness across various static and dynamic scenes. We also conduct ablation studies to explore the design choices in our model. For comparisons, we evaluate our model against both generalizable and non-generalizable view synthesis methods. We follow a standard evaluation procedure, using every 8th view as the target and excluding it from the input views. We average results within and across scenes, ensuring a fair comparison by adjusting the aspect ratio of the internal LDM dimensions to match our 1080p model's requirements. In our comparisons with generalizable methods like Simply, NRF, and GPNR, we retrain all baseline models using the same camera selection strategy. Our results consistently outperform these methods across all datasets, and we are the only method capable of real-time performance, being significantly faster than NRF. Our Quark Plus model shows improved reconstruction quality over Quark due to its higher resolution, while still maintaining interactive speeds. Section Summary. In this section, we describe our fusion block, which integrates one-to-many attention and convolutional blocks to effectively aggregate views and constrain the latent diffusion model, LDM, to real scene manifolds. We detail our training process using calibrated multi-view images, achieving significant performance improvements over existing methods, particularly in real-time rendering and reconstruction quality. Section: Non-generalizable methods. In this section, we compare our model to various non-generalizable methods, using standard benchmarks with published results. First, we look at the DL3DV benchmark, which includes diverse scenes captured by handheld mobile cameras and drones, featuring more complex camera movements than those from fixed setups. We find that our method competes well with scene-specific optimized methods. Even though we weren't trained on this dataset, we outperform top methods like ZipNerf and Gaussian splatting. Next, we evaluate our model on 12 scenes from MeepNerf 360, Tanks and Temples, and Playroom from Deep Blending. Our method ranks third on MeepNerf 360 and first on Tanks and Temples, while also surpassing Instant NGP and Plenixels on Deep Blending. A key difference between our approach and optimization-based methods is that we render the target view using only the 8 nearest input cameras, rather than optimizing across all cameras. For many benchmarks, these 8 cameras cover the target views well, but this isn't the case for deep blending. We found that adjusting our camera selection to consider viewing angle differences improves results, as nearby cameras can have varying angles. However, even with this adjustment, our method can produce artifacts when coverage is low, such as when only 1 or 2 distant cameras can see part of the target view. While per-scene optimization methods also show artifacts in low coverage areas, their outputs tend to be blurrier, whereas our method can create sharp, inaccurate edges. We believe that using a more advanced view selection method could help reduce some of our method's failures. For qualitative results, we present several examples of our rendered outputs that showcase high-quality reconstructions across various scenes. We note that differences between methods are more visible in video than in still images, especially when comparing Quark and Quark Plus. In our comparison with generalizable algorithms, we observe that NRF struggles with scenes that have significant depth complexity, likely due to its use of a single-layer depth map. Both Quark and Quark Plus produce sharper edges around complex geometries compared to NRF, simply, or GPNR. Quark's sharper results may be due to its use of image-based rendering with blend weights. In our comparison with offline non-generalizable methods using the DL3DV benchmark, we notice high-quality results but with some differences, particularly in reflective and refractive objects. We suspect that Quark's view selection allows it to optimize for a small number of input views, while other methods create a global geometry that may not accurately represent these challenging materials. Upon closer inspection of NRF-based methods, we see speckling artifacts common in ray-march rendering. Quark, Quark Plus, and 3DGS produce comparably sharp results, but Quark operates in real time, while 3DGS requires costly offline optimization. Finally, we compare to other offline non-generalizable methods using the MIPNERF 360 and Tanks and Temples datasets. We find that Plenixels yields blurrier results due to its sparse 3D grid representation. Quark, Quark Plus, INGP Big, MNERF 360, and 3DGS 30K show similar visual quality, with 3DGS 30K being slightly sharper. Quark reconstructs and renders in real time, while other methods take much longer. We also note that our metrics do not account for temporal flicker, and as shown in our videos, offline methods like NRF and 3DGS perform better in this aspect. Quark can switch between input images as the target camera moves, which can lead to noticeable flickering, especially with large exposure differences in the input images. Section Summary. In this section, we compare our model to various non-generalizable methods using standard benchmarks, demonstrating that our approach outperforms top methods like zip-nerf and Gaussian splatting, even without direct training on the datasets. We also highlight that while our method achieves high-quality reconstructions in real time, it can produce artifacts in low-coverage areas, which could be mitigated with improved view selection techniques. Section: Ablations. In this section, we conducted several ablations to assess our model design choices. We used the Quark Plus network as our baseline for these tests, but for efficiency, we trained on lower resolution data and limited our training to 250,000 steps. We evaluated the ablations on the DL3DV dataset at 1080p resolution, which is higher than our previous benchmarks. This higher resolution made the differences between the ablations more noticeable, even though the score variations were small. Many scenes in DL3DV are simple, allowing basic methods to yield satisfactory results. In more complex scenes, differences were often limited to a few pixels, particularly around object edges, resulting in minor metric changes. However, when we compared the results side by side, the differences became clear, and we encourage interested readers to check the supplemental material for these results. We present the percentage change in runtime compared to the baseline in a table, noting that these figures are approximate since the ablated methods were not fully optimized. For instance, in the no cross-attention ablation, we simply set the attention keys to 0. We performed the following specific ablations. 1. No layer collapse. We removed the layer collapse modules, which slowed the algorithm significantly but improved quality. 2. Baseline. This refers to the Quark Plus model trained at a lower resolution. 3. Fewer iterations. We reduced the number of iterations by omitting the first 2 update and fuse iterations, doubling the initial resolution to maintain output quality. 4. No ray directional encoding. We replaced the ray directional encoding with zeros to see its effect. 5. No cross-attention. We set all keys in the attention stages to 0, averaging the image update feature maps. 6. No render and refine. We replaced the rendered image with zeros to simulate the absence of this stage. 7. RGB output. Instead of blending input images for RGB output, we directly used the first 3 channels of the appearance feature from the network. Overall, these ablations highlighted the significance of our contributions, including ray directional encoding, cross-attention, render and refine, and our blend weight strategy. Interestingly, the fewer iterations ablation performed nearly as well as the baseline while reducing runtime by 17%, indicating potential trade-offs. Our network has many hyperparameters, and we couldn't explore all design options, suggesting that other configurations might achieve similar or better performance with lower runtimes. Future work could involve an automated parameter search. We also assessed our model's performance with varying camera baseline distances on the Spaces dataset, training a model that accepts between 4 and 16 input images. Our model showed robustness across small, medium, and large baseline settings, unlike Deep View, which performed best with small baselines. However, our SSIM metrics are not directly comparable due to slight differences in input preprocessing. Regarding limitations, while our method achieves state-of-the-art quality at real-time speeds across various scenes, it lacks temporal consistency in video reconstructions, leading to flickering artifacts. This presents an opportunity to explore temporal methods for smoother results. Although we use blend weights and image-based rendering for efficient high-resolution output, this approach has drawbacks. Blend weights alone cannot accurately represent view-dependent materials, as the colors produced are a mix from input images. However, our optimization of blend weights using ray direction encoding helps reproduce reflective and refractive surfaces convincingly. Blend weights also struggle with images taken at different exposures or focal lengths, causing visible edge artifacts and flickering. Additionally, errors in camera calibration can lead to incorrect edges instead of the desirable blurring seen in other methods. To maintain real-time performance, we rely on a limited number of input images, which works well when they provide sufficient coverage for synthesizing novel views. However, this is not always the case for certain datasets, leading to artifacts near the edges of the novel view. In such cases, a better view selection algorithm or a method that optimizes a single geometry across all images may yield improved results.